Hey everyone, and welcome to this explainer. Today we are unpacking some highly technical but honestly genuinely fascinating source material. We're tackling one of the absolute biggest bottlenecks in artificial intelligence right now, how to make AI radically more efficient. We're going to be looking at a brand new architecture called the P-spin glass network. If you've ever wondered how we're going to move from massive, energy-guzzling data centers to smart devices that actually learn right in the palm of your hand, well, you are going to find this incredibly cool. So, I want you to start by just taking a second and asking yourself this question. What if advanced AI didn't require supercomputers to learn? Imagine a world where continuous AI learning isn't entirely bottlenecked by massive server farms, but instead, it can happen locally, cleanly, and super efficiently. That is exactly the paradigm shift this source material explores. Okay, let's dive into this. Here is our roadmap for today. 1. The transformer bottleneck. 2. A physics-inspired AI solution. 3. Extreme AI memory compression. 4. The single batch breakthrough. 5. Processing tokens to raw bytes. And 6. The edge AI future. Let's jump into part 1, the transformer bottleneck, AI's massive appetite. To really understand the cure here, we first kind of need to understand the disease, right? Modern deep learning is fundamentally built on the transformer architecture. Now, while standard transformers are incredibly powerful, they totally hoard data. They rely on what's called large batch gradient accumulation. Basically, they need to ingest huge, massive piles of data in memory just to remain stable while they're learning. So true continuous learning on a small, low-resource edge device? It's essentially impossible if your AI requires a supercomputer's worth of memory just to learn one new thing without completely forgetting everything else. Moving right along to section 2. A physics-inspired AI solution, finding the minimum. The authors of our source paper are proposing a complete paradigm shift here. We're talking about moving away from brute force math and instead finding energy minimums. You see, standard architectures map inputs through explicitly unrolled feed-forward graphs, literally just multiplying massive matrices layer by layer. But the spin glass network? It uses implicit deep learning. Instead of forcing the math step by step, these implicit models define their hidden states as the converged roots of an iterative fixed-point solver. It's a radically different way of processing information. It finds solutions naturally rather than just forcing the math. Now, what's really interesting about this architecture is how it flows. On the input side, the left column, it's entirely modality agnostic, meaning it can take in subword tokens or raw byte streams. Then in the center, you have the hardware-fused continuous state space routing paired with the higher-order P-spin attractor search. Think of this as the engine room of the whole operation. And finally, on the right, you have the output evaluation. But the real magic? That happens right in the middle with the P-spin attractor search. That central engine relies on a really dense concept called a thermodynamic attractor. It's basically a physics-inspired equilibrium point where a system naturally settles into a stable energy minimum. Think of it kind of like a ball rolling down a bumpy hill. Instead of trying to painstakingly calculate every single bump it hits on the way down, the system is designed to just let the ball roll until it rests at the absolute bottom, the stable energy minimum. Structurally, this approach is just an elegant way to manage optimization variance. All right, let's hit section 3, extreme AI memory compression, shrinking the brain. So what are the concrete wins here? Well, the first massive win is an 8x compression. The researchers applied 1.58-bit ternary quantization, which honestly is just a super fancy way of saying they restricted the model's math to 3 simple numbers, -1, 0, and 1. Because the model is settling into physical minimums naturally, it literally doesn't need highly precise memory-heavy decimals. This targeted compression yields a massive 8 times parameter compression right in the equilibrium layers. But they didn't stop there. They also utilized the implicit function theorem, or IFT. This is a mathematical method used to extract exact analytical gradients right at that equilibrium point we just talked about. The so what here, the thing you should really take away, is that it mathematically bounds the activation memory. It completely decouples the memory needed from the number of microsteps taken to get to the solution. So no matter how many iterations the solver runs to find the bottom of that hill, the memory requirement stays strictly linear, no memory explosion whatsoever. When you actually combine all these innovations, fusing that state space chunking directly in SRAM, quantizing those projections down to just -1, 0, and 1, and applying the implicit function theorem, the real-world impact is absolutely staggering. The byte-level model footprint shrinks down to a hyper-efficient 41.37 megabytes. Just to put that into perspective, the uncompressed equivalent would be over 116 megabytes. Okay, section 4, the single batch breakthrough, the power of one. So, memory compression is great, for sure. But how does this thing actually train? Well, in standard deep learning, if you try to train with a batch size of just one, which is pure stochastic gradient descent, your optimization trajectory is going to be highly chaotic, full of variance and noise. But this brilliantly illustrates the difference. With the p-spin models, you get smooth, monotonically decreasing optimization compared to that chaotic baseline. Because the internal representation is forced into a stable energy minimum before calculating the gradient, it acts as a massive variance damper. The researchers prove something absolutely incredible here. To quote the paper directly, the architecture yields strictly smooth, monotonic convergence at a stochastic microbatch size of b equals 1. In plain English, this thermodynamic regulation completely eliminates the standard requirement for massive batch accumulation. It proves that stable, continuous knowledge retention is actually possible, just one single update at a time. Which brings us to section 5, processing tokens to raw bytes. Modality agnosticism. Now, let's look at how this performs against standard transformers. The subword p-spin model reaches the exact same baseline performance, a final loss of 4.8004 compared to the baseline's 4.8025. But here is the crazy part. It does this utilizing only 12.5% of the training sequences, just 8,000 sequences seen compared to 64,000. And because of the memory and batch size reductions we just went over, it functions at a blistering 0.44 seconds per step compared to nearly 19 seconds for the baseline. That is a real game changer. Furthermore, this whole framework is truly modality agnostic. It literally doesn't care what format your data is in. The exact same architecture can process a massive vocabulary of nearly 50,000 discrete subword tokens, or it can chew through uncompressed continuous raw bytes with a vocabulary of just 256, and it maintains robust temporal credit assignment across both. The sole algorithmic difference between the two configurations is simply the final mathematical projection. Finally, let's wrap up with section 6, the Edge AI future, continuous learning everywhere. So the crucial point is bringing all these highly technical breakthroughs back to their real-world impact. By stripping away the bloat and stabilizing single-batch training, the p-spin glass network acts as the ultimate antidote to AI bloat. If standard transformers are massive, gas-guzzling cargo ships that require incredibly deep harbors to function, this new architecture is like a hyper-efficient electric sports car. It establishes a genuine mathematical foundation for true continuous learning on memory-constrained edge devices. I want to leave you with this one provocative question. We've just seen how physics-inspired attractors and extreme compression can make a 41 megabyte model stably learn one piece of data at a time. So what does the world look like when every smartphone, every smartwatch, every single local device can constantly train and update its own AI without ever needing a server farm? That decentralized, continuous AI future might be much, much closer than we think. Thanks so much for joining me on this explainer. Keep learning, and I'll catch you on the next one.